All right. So, end of last class, we had practice problem number 4, where we were given a table and we were given several weird function formulas. We had to do the derivative with the function formulas and then use the numbers from the table to evaluate the derivative at that number. So we did 2 of those. And then we did another one that had a derivative of e to the x in it. So I want to make sure we do one of the particle moving along a line, which is problem 5. So we've got, suppose that a particle moves along a horizontal coordinate line in such a way that its position is described by the function blah for 0 less than t less than 3. So these first 3 parts, we're still going to ask on the test. What's the velocity function? What's the acceleration function? Where is it moving, right versus left? And then this asks about the intervals for where it's speeding up and slowing down. We're not going to make you do the full intervals for speeding up and slowing down. We're just going to ask you to figure out if it's speeding up or slowing down at one particular value, which is less work, but you still have to understand the whole speeding up and slowing down part. But either way, our first step is figure out the velocity and acceleration functions. So velocity is the first derivative. So I have the 16 thirds, and then the derivative of t to the third will be 3t squared minus 24 times the derivative of t squared is 2t to the first plus 32 times the derivative of t is 1t to the 0, but t to the 0 is just 1. So really the derivative of 32t is just 32 plus the derivative of a constant is 0. So there's our like long written out derivative. Now let's simplify it a bit because we're going to have to play around with it. So here, the ugly 16 thirds we started with interacts nicely with that 3 that came down. So we have 16t squared. Minus 24 times 2 is 48t plus 32. So we have our velocity function. Now, if our position function was measured in, let's say, inches, and the time was measured in seconds, then what would the units be for the velocity? Yep, inches per second. Now, to answer where is the particle moving right and where is it moving left, we need to figure out where is the velocity positive, where is the velocity negative, which that amounts to positive is greater than 0, negative is less than 0. So that means if we figure out where it's equal to 0, those are our turning points for where it changes direction. So we are going to set this equal to 0. So on first glance, that function is disgusting. Those numbers are really big, but all of those numbers are actually multiples of 16. All of the numbers here are divisible by 16, so I can actually factor out 16 as a common factor. But if you don't notice that, you can still do the quadratic formula with the big numbers. It'll work. You just got to be careful that you don't misplace stuff, but it will work out. But if you happen to notice that they reduce, it makes the quadratic much easier to work from. So 48 divided by 16 is 3. 32 divided by 16 is 2. So we actually have 16 times t squared minus 3t plus 2. And then when we have just a t squared, that has to factor into t and t. 2, well, there's only one way to get two numbers that multiply to 2. 2 times 1. Well, not only one way, but only one way with integers. And then if I make them both negative, t minus 2 times t minus 1, that would be t squared minus 2t minus 1t would give me minus 3t. Negative 2 times negative 1 would be positive 2. So this FOILs out. That is our factored form. Now that it's factored, I can set each of the factors equal to 0. So we technically have a initial silly statement of 16 equals 0. Yeah, that never happens. Then we have t minus 2 equals 0. So that gives us 2 seconds. And t minus 1 equals 0, so that gives us 1 second. Now, the original problem limited our time from 0 to 3 seconds. So that's why I put 0 and 3 on my number line. And then the 1 and the 2 we found are the other numbers. So now we just have to figure out what the velocity is doing between each of these numbers. So I'm going to pick some test values, but I'm going to plug these test values into the factored form. Well, I can't actually pick 0 and 3 as test values because the only actual turning points are 1 and 2. But I also need to pick a number between these two. So we'll go with 1.5. So plugging in 0, 0 minus 2 is negative 2, 0 minus 1 is negative 1, negative 2 times negative 1 is positive. So everything to the left of 0 is positive velocity. Sorry, everything to the left of 1. Then if I plug in 3, 3 minus 2 is 1, 3 minus 1 is 2. Those are both positive. So everything after 2 is also positive. Now when I do the 1.5, 1.5 minus 2 is negative. 1.5 minus 1 is positive. Negative times positive is negative. So everything in between 1 and 2 is negative. Mm-hmm. So we know this is, like, the original function was 16 thirds t cubed. So that is going to end at infinity. And if it's got two turnaround points, then it actually changes. So it's going up, then going down, going up. Yeah. All right, so let's look back at the question. So it asks, where is it moving right? So right here is going to be the positive direction because it's moving on a number line. So it's moving right from 0 to 1 and from 2 to 3. And I'm using the 0 and 3 as endpoints because that's what they gave me. In fact, in the original setup, they did not include the 0 and the 3. So we should actually have parentheses on the 0 and the 3. Now, if you guys accidentally put brackets versus parentheses on the outside points, that's all right. But the 1 and the 2 for sure should have parentheses because the velocity is 0 there, so it is neither moving left nor right at 1 and 2. And then our left will be from 1 to 2, the middle part. All right, now we also need the acceleration function. So I'm just recopying my velocity function. And then acceleration is the derivative of velocity. So that'll be 16 times the derivative of t squared is 2t minus 48 times the derivative of t is 1 plus the derivative of 32 as a constant is 0. So we get 32t minus 48. Now, to answer about speeding up and slowing down, we need to know when the acceleration is positive, when the acceleration is negative. So we need to know when it's 0. And we end up with 1.5. All right, so if I plug in 0 into my acceleration function, I get 32 times 0 minus 48, so I get a negative number. So everything before 1.5 is negative, and then everything after 1.5 is going to be positive. So the last part of the question was asking about speeding up and slowing down. So to answer about speeding up and slowing down, we've got to collect the data from both number lines. Now, on the test, you don't have to answer the overall intervals. It'll just be like, what's it doing at 2.5? So at 2.5, you can figure out the velocity by plugging in the number. It's positive. Acceleration at 2.5, you can plug it in. It's positive. They're in the same direction, so it's speeding up. All right, so in our first section from 0 to 1, my velocity is positive, but my acceleration is negative. So from 0 to 1, since they're different signs, this is slowing down. Now my next one, my velocity has changed to negative and my acceleration is still negative. So now it's speeding up. Then 1.5 to 2, my acceleration flipped to positive, but my velocity is still negative. So now it's slowing down. And then from 2 to 3, the acceleration is positive and the velocity is positive. So now it's speeding up. The slowdown is from 0 to 1 and from 1.5 to 2. And then speed up is from 1 to 1.5 and 2 to 3. So again, you're not going to have to do the full speed up, slow down comparison. You'll just have to do it for one number. But you are going to have to tell me when it's moving right and left. So questions on this problem? Yep. So it's like positive acceleration is when you're pushing down on the gas. Negative acceleration is when you're pushing on the brakes. but the velocity direction is also changing here. So it's not just a matter of like you're driving forward. There's also, yeah, like, so that's why, like, that's where the car analogy kind of breaks down.
So from 0 to 1, how do I know it's moving from eight?
Because when we plug in a test value for all the numbers left of 1, which I plugged in 0 into the function, like the velocity at 0 would be positive 32 because we'd get 0 minus 0 plus 32. So since 32 is positive, everything in that interval has to be a positive velocity. Because we know at 1, it becomes 0. So it doesn't change anywhere to the left of 1. So if I pick one number in that interval, that's a placeholder for everything in that interval. I just like talked through plugging in the number instead of writing it down. But I had to pick a number between 1 and 2. You can also, though, just use like your knowledge of the way parabolas work. So this parabola, like, it's 16t squared, so that means it opens upward. So it's like above the x-axis, below the x-axis, above the x-axis. So you could also like just be like, all right, in the middle, it's going to be negative. The other two are going to be positive. All right, the other problem I want to make sure we do is doing an implicit differentiation question. All right, so the coefficients on this one are stupid looking. The coefficients won't be that stupid looking on the test, but the function here is not a bad one. All right, so we want to figure out the equation of the line tangent to this graph at the given point. So that point is an x value and a y value. So to figure out the equation of the tangent line, I have the point. I need to know the slope of the tangent line. Slope of the tangent line comes from the derivative. So we are going to take the derivative of that crazy looking function. All right, so when I take the derivative of the first part, the constant's going to carry through, so I still have the 32 over 65. The derivative of x to the third is 3x squared. And that's x, so we don't have to worry about dx. Plus, same idea, 32 over 65. The derivative of y cubed is 3y squared, but since this is a y, we're also going to have times dy dx. Minus 8 times, now we've got the derivative of xy. So that is a product rule. So I'm going to put this in brackets because that -8 is going to have to distribute through my result from the product rule. So derivative of the first one, derivative of x is 1 times keep the y plus keep the x times derivative of y is dy dx. And then equals derivative of 0 is 0. All right, so now what we want to do is we want to solve for dy dx. So first thing I'm going to do is a little bit of cleanup, multiply our numbers here. So 32 times 3 is 96. So we have 96 over 65 x squared plus 96 over 65 y squared dy dx minus 8y minus 8x dy dx equals 0. All right, so to solve for dy dx, everything that has a dy dx I want on one side. Everything that does not, I want to throw to the other side. So I'm going to add this 8y. I'm going to subtract this front term, the 96 over 65 times x squared. Right now, our terms with dy dx are isolated, so we can factor out dy dx as a common factor. We divide by the crap. So we now have a formula for dy dx. So that's the first part of what they're going to ask on the test, because we do ask you to find dy dx. But the actual question was, find the equation of the tangent line. We need the slope of the tangent line, but we have the point 4, 1. So I'm going to plug in 4 and 1, 4 for my x's, 1 for my y's. So we have 8 times 1 minus 96 over 65 times 4 squared all over 96 over 65 times 1 squared minus 8 times 4. And then this is the point where use your calculator. That is stupid looking to mess with by hand. So 8 minus 96 over 65 times 16. And then 96 over 65 is 32. Sure. So 127 over 248. Sure.
I'm confused about the early stuff. So when we distributed like the -8 and we're left with like the giant function and then do we move stuff over like to the zero side? Hold on, wait. It's because I'm getting a -8y and a positive 8x. So the positive x squared and then the y squared. And I don't really know that it was.
All right, so with my setup, I chose to move minus the 9665x squared and I added the 8y. But if you moved the dy dx terms instead, then they'd end up on the other side and the signs would be a little different. But like, if you look at like the result I had and you multiply by -1 over -1, like all the signs will flip and then it should look like the answer you got. So yeah, they're equivalent. All right, now we still need the equation of the tangent line. But we've got the point, we've got the slope. So y minus y1 equals m times x minus x1. Y1 is the number 1. M is annoying 127 over 248 times x minus 4. Now for the test, stop right there. That's good. For web work, we're going to have to distribute and then add the 1.
What work, you can just add the 1.
Oh, you can just like
You can
write
just
it.
do
Okay. I mean, honestly, working this one out, this one might be a little long. No, that's about what the function was before. But without the stupid coefficients. All right. Everything else on the test is just derivatives. So derivatives with product rule, quotient rule, a lot of chain rules, and then the weird functions that we learned about. So now it's those of y'all that have looked at the practice problems, were there any of the practice problems in particular that you wanted me to go over?
There one that includes product and chain.
I haven't written out the details of the test yet, so maybe. There's definitely some that'll be like multiple chain rules. Yeah. So let me do, yeah,
Oh,
I can find one. All right, but we also had somebody ask for 25, so let's start with 25 because that's also a chain rule. It was 25, right? Yeah. All right, I have no idea why it says where A is any positive real number. Because there's no A. All right. So I've got a function that has a natural log, but then the overall operation there is a plus. So I can't use any log properties to break this down. So all we're doing here is just using our derivative of natural log to do the derivative, but I'm going to rewrite it a little before we do the derivative. Instead of 4 over x, I'm going to write it as 4x to the negative 1. So now it's set up to do a power rule, so it's a little bit easier to look at. All right, so now we're going to take the derivative. So the derivative of natural log of ugly is 1 over ugly times the derivative of ugly. So 1 over, copy what's inside exactly as it appears. Times, now we're going to do the derivative of the inside. So the derivative of 3x squared is 3 times 2x plus 4 times the derivative of x to the negative 1 is negative 1x to the negative 2. Now, for the purposes of the test, like, that's good. And even for web work. Like a pain to type, but yeah. Now we could like clean it up a tiny bit. So that is 6x minus 4x to the negative 2 all over 3x squared plus 4x to the negative 1. 1, not 2. But for the test, that first one is easier for me to grade. I can clearly see like you did the natural log derivative times derivative of the inside. Yeah, like the directions on all the derivative questions say you do not need to simplify. It is easier to grade it if you don't simplify it.
Well, that's another, derivative of natural log.
Yeah. The only formulas that are provided on the test are the derivatives of the inverse trig functions.
The, are those gonna be on the?
You mean the derivative of the So you have to know the derivative of all the regular trig functions.
What about like?
Yep. So those are the only formulas you're going to get on the test. Now you're not going to have to use all 6 of those. You might only have to use like 2 of them. And it probably won't be the last 2 because we tend to avoid those. All right, let's see. So here we go. This is a trig function, and then inside it is a product, and then inside that, we're even going to have a chain rule. So we've got a chain rule product chain rule. All right, so when we go to start doing our derivative, we do the derivative of the outside function, which is sine. So derivative of sine is cosine, so I'm going to have cosine of, keep the inside the same, times, now we're going to do the derivative of the inside. Now our inside is a product rule. So we got an A and a B. So my x to the sixth, derivative of that is going to be 6 x to the fifth times, I keep b the same, so e to the 2x, plus, now I keep x to the sixth the same, times the derivative of e to the 2x. Well, the derivative of e to the something is e to the something. But then our something isn't just an x, so we're going to do the derivative of the something. The derivative of 2x is just 2. So there's like a whole lot of thinking on these, but not necessarily a whole lot of writing. Like, can you, I mean, like you could just write the 2 in front. So yeah, if you like look at this and you're like, oh yeah, it's going to be multiplied by 2. So you just write 2 x to the 6th, e to the 2x, or you wrote it 2 e to the 2x, x to the 6th. Like, yeah, any of those are fine.
What rule is the one that makes you multiply like the original parentheses function times the derivative?
So the chain rule? Yeah. So whenever we have like a function and then we've got stuff inside the function, that outside inside, that's our chain rule. So the chain rule is just the derivative of a composite function, a function inside a function.
Does we have a chain rule inside of a rule?
Yes, maybe. I haven't written the whole test, but my colleague put it on his test, so maybe. So let me see if I can find one in the practice problems. So it looks like 24 is a double chain rule. All right, so doing our derivative, I have e to a power, and then my power is tangent of a thing. So there's our like double chain rule, e to a thing and then tangent of a thing. So still we focus the outermost function first. So e to the thing, derivative of e to the thing is e to the thing. So we'll have e to the tangent 5x times, now we do the derivative of tangent 5x. Well, the derivative of tangent is secant squared. So we'll have secant squared of thing. Times, now we do the derivative of what's the thing? The derivative of 5x is 5. So a lot of these derivatives, it's about taking a moment to look at the function, analyze the structure, and see which pieces are fitting together, what rules that means you need to use. Twenty-three is another good example of a double chain rule. So this one, they've given us two different functions, but they've changed the order of the functions. Well, and then they changed the inner one as well. But both of these have arctangent and natural log. It's just what's on the outside versus what's on the inside. All right, so I went and grabbed a picture of the derivative of inverse tangent for us to make use of. All right, so when you're making use of these formulas, the formulas are written in terms of x, but our function here is written in terms of ugly. So when I have my setup here in terms of x, I can also think of it as a chain rule. All right, so our outermost function for f of t here is arctangent. So I'm going to use my derivative formula. So it's going to be 1 over 1 plus thing squared. Thing is natural log of t to the 7th. Now we're going to multiply by the derivative of the natural log of t to the 7th. Now, you don't have to write this step in here. If you're comfy just like writing the derivative in there, you can do it that way. I'm just trying to break it down to remind us how the chain rule works. So I followed my format, the 1 over 1 plus thing squared times derivative of thing. Now, the derivative of natural log of something is 1 over something times the derivative of something. The derivative of t to the 7th is 7t to the 6th. And that right there is easiest to grade. So in my brain, it's totally logical to go from the function to just writing the derivative, that last line I have here. All right, is there another one in there y'all want to look at?
Second part of it.
Sure. All right, so we've got our natural log is the outermost function, then our inverse tangent, and then 5t. So when we go to do our derivative, our natural log says derivative of natural log is 1 over ugly times the derivative of ugly. So 1 over ugly is inverse tangent of 5t times, now we're going to do the derivative of inverse tangent. Well, that's our formula that we have over there. So derivative of inverse tangent of thing is 1 over 1 plus thing squared. Thing is 5t. And then times the derivative of the thing, derivative of 5t is 5.
Doing the implicit one.
Another what?
Implicit.
Sure. Yeah, this one's not bad. Yeah, you just put it on top. Now on the test on the implicit, it is going to ask you to find the slope of the tangent line at a point and then write the equation of the tangent line. But for just practicing the implicit, like this works. And this is closer to what it would look like on the test. On the test, I'm not going to put those stupid coefficients that other problem had. All right, so x to the third times y, that is a product rule. So derivative of the first part, x cubed, will be 3x squared times, we keep y the same, plus, now we keep x cubed the same, and we do the derivative of the second part, which is dy dx. Minus 3, the derivative of 3 is 0, because it's a constant, equals, now the derivative of y is dy dx, minus the derivative of a constant is again 0. So even though the initial equation looked kind of weird, like the constant's just gone. All right, so I've got two terms with dy dx. I'm going to minus the x cubed dy dx to the other side. So I have 3x squared y equals dy dx minus x cubed dy dx. They both have a dy dx, so I'm going to factor that out. And write my leftovers. So dy dx was the only thing in the first term. So I'm going to put a 1 as a placeholder. So that way dy dx times 1 gets us back to dy dx. Minus the x cubed will be inside. The dy dx is factored out. And then last step, we divide by the other stuff. $17? Yeah, 17. That's probably closer to how it'll look on the test. None of those stupid coefficients. Yes, when we factored out dy dx. So I put 1 there so that way, because dy dx was the only thing in the first term. So that way dy dx times 1 would be dy dx. If I distributed back, it would re-equal what we had before. If I don't have the 1 there and I just write negative x cubed, then all I've taken care of is that second term, and the first term has just disappeared. So that's why anytime I factor out a common thing, I'm always in the back of my head thinking like, is this going to multiply back to the previous line? Did I do my factoring correct? All right, is there another one that you guys have that you'd like to see?
I'm gonna post that like list of where the questions come from. For this.
So the first question is going to be that table question, which was, yeah, web work practice problems, question 4. Question 2 and question 3 are just going to be various derivatives. So there should be like probably 5 of them. And there'll be like some product rule, some quotient rule, some chain rule, like trig stuff, natural logs, e to the x's, like it's all the jumble crazy mix that you see in most of the practice problems. Question 4 is going to be implicit. With finding the equation of the tangent line. And then question 5 was the velocity and acceleration. Now the table question will have several parts, so it'll, there's like 3 different derivatives. All right,
For Friday time?
there is not. The practice problems are more than long enough.